Guys, welcome to this new video. So now we're going to go through this question 8 from the May 18 Time Zone 1 paper 3, and it's a rigid body mechanics question. So here we are told that a constant force of 50 newtons is applied tangentially to the outer edge of this merry-go-round, and this diagram shows this situation from the above view. And we're told the moment of inertia of this merry-go-round, and we also told the diameter of 4 meters. So we first need to show the angular acceleration of the merry-go-round. So this is the typical equation here. We know that the torque is equal to the moment of inertia times the acceleration. We need to calculate the torque. We know the moment of inertia, so we can easily calculate the angular acceleration. And well, the question is, what is the torque? So over here, this 50 Newton force is what is producing the torque. It's what's making everything rotate. So we need to see the arm of this force. So we need to see the distance of this force from the axis. The axis of rotation is this middle point. So we need to draw a perpendicular line and see what this distance is. Well, we just see that this is the radius of the circle, which is 2 meters. So the arm of the force is going to be 2 meters. So the torque, which is 50 times this 2, will be equal to the moment of inertia, 450, times the acceleration, which we want to find out. And if we do this, we'll find an angular acceleration of 100 divided by 450, which is 0.22, which is approximately 0.2 radians per second squared. Alright, and now we are told that the merry-go-round starts from rest, and this force is applied for 1 complete revolution. We need to calculate after 1 revolution the angular speed. So during this motion, we have a constant acceleration, as this torque is constantly making it rotate with a constant distance from the axis. So here the acceleration is constant, so we can use the Suvat equations, and well, we know that the final speed squared is equal to the initial speed squared plus 2 times the angular acceleration times the change in angle. And well, we know that the initial speed was 0, so we can say that our final speed squared, what we want to find, will be 2 times this acceleration we have, times by the angle swept. And well, in 1 revolution, we cover 360 degrees, right? But in these equations, we always need to substitute in radians. So 360 degrees will be 2 pi. So we have covered a distance or an angle of 2 pi here. And well, if we take the square root of this, we'll find a speed of 1.7 radians per second. And we also need to find the angular momentum after 1 revolution. And well, angular momentum is just the moment of inertia times the angular speed. So we just need to plug it in. Our moment of inertia was 450, and we just calculated the speed to be, well, 1.7, approximately 1.7. Although this, I believe, is a rounded value. More precisely, it would be 1.66 radians per second. So in these questions, we can usually use a more precise value, and then our final answer we can round. So this will be approximately 750. And then the units of angular momentum would be kilogram meter squared, that's moment of inertia, and radians per second for angular speed. Now we are told that a child of mass 30 kilograms is placed onto the edge. No external torque acts on the system, and we need to calculate the new angular speed of the rotating system. So what is happening here is we just take a child, place them on the edge, and make it rotate, and we need to see what the new angular speed of the merry-go-round will be. So what's important here is that like the center of this child will be 2 meters from the center of rotation, as we're placing her on the edge. So firstly, we need to calculate the new moment of inertia. We know moment of inertia is just the sum of mass times the radius squared. So we know that without the child, our moment of inertia was 450 kilogram per meter squared. But by adding this child, we added a point mass to the edge of the merry-go-round. And this child has a mass of 30 kilograms and is a distance of 2 away. So we need to take the child's mass and multiply it by the child's distance squared from the axis. That will be the moment of inertia of the child around this axis. And well, since these are the disk and the child is like one system, we can add their moment of inertias to get the total moment of inertia of the system. So our new moment of inertia will be 450, the initial one plus the moment of inertia of the child's mass times the distance, so it's 30 times the distance squared, so 2 squared. This will give us 570 kilogram meter squared. And well, we know that we are told that no external torque acts on the system. This means that angular momentum is conserved. As if there are no external forces, momentum is conserved. Also in mechanics, the linear mechanics, like this. So that means that before we place the child onto the merry-go-round and after we place the child on the merry-go-round, our angular momentum did not change. So, well, we know that before our angular momentum was 750. So now we also need an angular momentum of 750, but now we have increased our moment of inertia to 570, and so our speed will also change. And well, our speed will just be, if we divide these two numbers, 1.3 radians per second. And then now we are told that the child moves towards the center, and we need to explain why the angular speed will increase. Well, we can just assume, well, we know that the moment of inertia of the system will become smaller and smaller, as this 2 here will become smaller and smaller, so we'll be adding a smaller number to 450. So as the child moves in, our moment of inertia will decrease. Moves in, or I decreases, like this. And since our angular momentum is still constant, as we are in an isolated system, no external torque acts on the system, so angular momentum is conserved, as there are no external forces. Then similar logic as the previous one. So if we have a constant angular momentum of 750, but we have a smaller and smaller moment of inertia, then our speed must increase. And that's pretty much it. So then our speed must increase. So that's why it will increase. And then we need to calculate the work done by the child moving from the edge to the center. And well, so when the child is in the center, what we need to notice is that this 2 meters will become 0. So when the child is over here, the child will be a distance of 0 meters from the center of the from the axis, meaning it will not contribute any moment of inertia to the system anymore, as the moment of inertia is the mass times the radius squared. But the distance, the radius, is just 0 here, so no extra moment of inertia here. So when the child is in the center of the merry-go-round, we assume to have the initial moment of inertia. And if we have the initial moment of inertia, that means our speed is 1.66, as angular momentum is conserved, as we just discussed. So if we want to calculate the work done, we can calculate the work of the system, well, the change in the energy of the system, the rotational energy of the system. So we can do just the final E kinetic minus the initial. So the final well, these are all rotational energies, obviously. So we need to use the formula of 1/2 moment of inertia times angular speed squared. And so our final is when the child is in the center. Then we have original situation, so just 1/2 times the initial moment of inertia times the initial speed of 1.66 we calculated here. So if the child is in the center, it's like the child is not even there, like this. And then we need to subtract from this the rotational kinetic energy of the system when the child is at the edge of the merry-go-round. In that case, we have a moment of inertia of 570, and we had a speed of what we calculated of 1.3. And so we need to multiply this by 1.3 squared. And if we subtract these two, we get an answer of 131 joules. So this is how much work the child did to move from the edge to the center. So this was the end of this question. I hope I was able to help, and see you in the next video.